Okay, so our last talk of the conference is by our own Radek Wojciechowski.
We're just practicing.
Radek Wojciechowski from York College and the Graduate Center. The title of his talk is Stochastic Completeness of Graphs 10 Years After.
So thank you for the introduction. We've heard, very many nice tributes to Józef during these 2 days. So, it's hard for me to put into words how much he means to me, but, I can say on a mathematical level, I think he really has this ability to kind of take kind of deep and difficult things and kind of explain it in a way that's very approachable, at least for me. So I think I think when we started working together, we would read papers, and I had this impression that you should kind of try to understand everything, kind of read it linearly from the start, and he would, he would like show me where the key thing was and kind of explain that to me, and then kind of read out from there, and I thought so I think this taught me very much, and he has really a way of kind of explaining something that I think is quite deep in a way that I could understand at least. So I really appreciated this, and I think also just on a personal level, he's always been extremely supportive towards me, and I know many other people as well. And he's very calm always. but if there's any issues, you kind of sense like he will take action. So it's very nice to have such a presence, like such a strong, like very calm presence. But you know that he will like always support you no matter what. So I think these two things I would like to say, and yeah, a lot of this is about just. So my talk, I know it's the last talk. I did the schedule, so I put myself last. But anyway, so I'm going to mostly just tell some stories and also some math stories. What else would I want to say? Maybe I can tell a little bit about the history also. So some people did this. So I actually came here in 2001, and I met Józef. He was the outgoing executive officer that year, so he kind of introduced me we got introduced at the kind of student orientation, and then he sort of left for a couple of years. I didn't see him, and I think the graduate program here can kind of counts on students to be somewhat self-motivated in terms of structuring things. So I think there was a year or two where I drifted. I passed all the qualifying exams the first year. Maybe the second or third year, it wasn't really clear to me what I was doing or who I would work with or what I would work on. And I think there was a conference for Edgar Feldman's retirement one year, and I came to this, and Józef was there, and we kind of ran into each other in the hall there and just kind of had a short interaction. I thought, maybe he can kind of help guide me because I'm not sure what's going on at this point or what I should be doing. And then we started, so then I just emailed him, can we meet and talk? And this is kind of how we started working together. And we worked on something totally different at first. We worked on L2 Betty numbers, which there wasn't any talks about at this conference, but this is another area that Józef has really significantly contributed to. So we worked on this. And I'll tell one funny story here about working with Józef. So he has this system where we meet every week, which was really good because even, there are times when I was teaching or other things were in the way, but the night before the meeting, I had to really prepare. Even that night, I was like, I have to get some questions ready to ask him. And the great thing was that, we would always meet, but he oftentimes wouldn't remember what we had talked about the previous week. So I could ask him the same exact question next week. And this was really great because I understood a little bit of the response, and then I could come back and he wouldn't say, didn't I already explain this to you? I feel bad about asking the question. He would rather start from the beginning and kind of tell me again, and then I would understand a little bit more. So this was really nice. So yeah. Sorry if I give anything away. But there was even a funnier time where I think we were reading this paper about these L2 Betty numbers, and it was maybe the first time where we were kind of stuck in reading the paper, and I understood something before he did, and I explained it to him for once, and I was really happy. And then maybe 2 days later, this was kind of towards the end of the semester, maybe 2 days later, there was end of the end of the year party in the department in December that we always have. And we were hanging out, and he kind of came up to me and said, I understood that part of the paper, let me tell you about it. Like, took me to his office, and he started explaining it to me, and I was like, wow, like, I explained that to you 2 days ago. I didn't say it, I just let it go. Because I didn't want to give up the trick that I've been using all this time to so this was really sweet. So I thought, this was really great. So this is a funny story. And then, so we worked on these L2 Betty numbers, and at some point, I think about 2005, after the summer, he said, I have this idea for what we can work on graphs. It has to do with the heat equation, and I think I don't know much about graphs or the heat equation. And he said, no, it's no problem, you will learn. So, and I thought this was such a definite statement that I was like, okay, I will learn that. And it was true. And this, so I want to tell a little bit of the story about what's happening. So this was 10 years ago. Defended in December of 2007, but I deposited in 2008. It's been about 10 years. So I want to kind of tell a story about the things that are in my thesis and how it has proved to be very fruitful. So, because afterwards I thought I would do something different, but I keep kind of coming back, and I'm still very much milking the ideas there, and many of the ideas and kind of suggestions for the problems and for how to go about them came from Józef, so I think this is really a tribute. So I'll tell a lot of stories, obviously, like I said. So, okay, so here's just the title page of my thesis. I scanned it in. It's in the math department there. Though the math department one has these, so yeah, let me go to the next slide. So this is the signature page. So I want to tell a story about this. This is very funny. So what happened is, like I said, I defended in 2007 in December, but then I didn't have the signature page ready. So I didn't get the signatures at the time of defense. and this is something that people at CUNY would find maybe strange, but at CUNY, if you're here, you know what this means. So there's Isaac Chevelle and Leon Karp. They're at different places, and they weren't coming here so regularly. So I think when it came time to actually get the signatures, I think you had to go to Isaac's house for dinner, and I had to travel.
I didn't get dinner, but I did get signatures.
Okay. But you had to make a journey, and then I had to go up to Lehman and like really go meet Leon Karp. I mean, I think there was one time with Leon. It wasn't for this, but it was for my oral exam form, where I had to get a signature, and he said, oh, I'll be passing through this subway station at this time, and this is how we did it. I mean, I left the graduate center, I walked over, and it was over a turnstile. I mean, I didn't even go in, I just passed him the form, and he signed it and gave it back to me. So I think this is very CUNY. We're not like very centralized, this is very much so. So this is kind of some funny stories about this. And this actually has the original signatures, because there's 2 copies that you have to get the original signatures, and then you get three sort of duplicates. And this one is in the library. This one is the original. The one in the math department is actually one of the duplicates, because I kept one of the originals. So hopefully that doesn't discredit.
So Józef wore many hats there.
Yeah. This is also true. You see, he appears 3 times. So, yeah, exactly. I think this is. Yeah, he's still doing this. Okay, so let me now get to some math things, but I will still tell many stories along the way. So there are sort of three questions, I think, in my thesis. So there's about this unique self-adjointness, which is called essential self-adjointness of the operator. So I'll talk a little bit about this, and then this is kind of the bulk of it. So it's about the heat equation. And does it have a unique bounded solution? So if you have a bounded initial data, does this uniquely determine your solution? And there's this question about the bottom of the spectrum and the essential spectrum, which Matthias talked quite a bit about, so I will not really talk about this so much, but these were kind of the 3 things in my thesis. All 3 of these turned out to be very good questions that have not really been asked so much for graphs, and I'll kind of talk about why a little bit, and like I said, a lot of new ideas came along. And one thing I'll say is, I mean, all of these questions were quite studied for manifolds, Riemannian manifolds, and so you kind of know what to expect. And you could just take the proofs in manifolds and kind of go line by line and copy them and kind of make the necessary alterations. The good thing is that it didn't prove to be so straightforward. And this is actually good in this sense, because otherwise there wouldn't be much of story to tell. You just do it and you're done. But actually, there was a lot of new things which I'll talk about. I think Matthias pointed out with this Cheever constant. This is a long story. This is one thing, but both the stochastic completeness and this essential self-adjointness proved to be quite fruitful. I'm still kind of interested in these things and still working on them. And another nice thing, I mean, these three questions sound different, but they can all be kind of discussed in terms of what are called lambda harmonic functions. This is like eigenfunctions, but this is, you don't necessarily, this function v should be in some different kind of spaces. So all three questions can be thought of. You look at this equation, and the first question can be addressed as saying there should be no solution to this in L2 in the square sum of functions for lambda negative. And then here I should say up front that my Laplacian is a non-negative operator. And the second question, even though it has to do with the heat equation, which has to do with time and things, but there's no time here, but you can rephrase it in terms of no solutions and no bounded solutions for lambda negative. And the third thing is with this positive bounded spectrum. This I learned from a paper of Sullivan that you can, but it goes back to Allegretto-Piepenbrink, that you look at positive solutions for actually lambda positive. So all three of these problems, though they seem kind of different, can be addressed with this one equation and looking at solutions. And like I said, I will kind of talk mostly about the second problem. This is what stochastic completeness has to do with. I'll talk a little bit about the first problem because we kind of did them in this order. And actually, we didn't realize, this really proved to be a fruitful perspective on all three problems. And I'll talk about how this is. So let me just set up the setting, which Matthias already kind of had. Just a infinite locally finite connected graph. So and you have a vertex set, which here is countably infinite. Same notation as Matthias. You have vertices that form an edge. I'll use this notation, and I'll say that they're connected or neighbors. Local finiteness means that each vertex has only finitely many neighbors, and the degree is the number of neighbors. So this is all very standard. Again, connected just means you have a path between any two vertices, and then you have this natural path metric that arises that Matthias also talked about, where you look at, so I'll call this the combinatorial graph distance. So you look at the sort of minimum number of edges of any path connecting two vertices. So I'll assume that the graph is connected, so this is all good. So here's the Laplacian, which will play the main role. So again, this is the same thing that appeared, well, Matthias had two different Laplacians. This is the unnormalized one, which, again, initially we weren't sure which one to look at, but this turned out to be the one which is interesting for these questions. So here, again, just setting up some notations. I have finitely supported functions in L2. This is a Hilbert space with the standard inner product. So here, again, Matthias talked about that you have a choice of measure for your Hilbert space. So here the measure is the counting measure. Every vertex, it doesn't distinguish between vertices. Every vertex gets measure 1, so that's why you don't really see it here. And again, there's no normalizing factor out front here, so this is in general an unbounded operator.
Normalized would have been the valence or something?
Yeah, you divide by the degree.
Right.
Yeah, so you take 1 over the degree of x here. And like I said, that operator turns out to be always bounded, as Matthias said. It's always bounded above by 2. This one might be bounded, might not be bounded, which I'll point out in a minute. So those are the two standard choices that you get in this setting, and I'll just look at this one. I won't talk about any other one. So again, now you restrict this kind of formal operator to finitely supported functions. You can ask, does it have a unique self-adjoint extension to an operator in L2? And if so, then the Laplacian is said to be essentially self-adjoint. So this is a basic question of functional analysis that you can ask, and surprisingly wasn't asked before. But yeah, I think Józef asked me this, and it turns out that it always is, and here's the proof, which actually, like I said, because this perspective is you can have this perspective for all three of these problems. This was kind of the starting point, which gave a good insight into how to approach these other problems. So you look at this kind of equation, and you look at kind of solutions for lambda negative, and again, so essential self-adjointness, this uniqueness of self-adjoint extension is equivalent to the non-existence of non-trivial solutions to this equations in the domain of the adjoint. The first thing is, what is the domain of the adjoint? Again, I take the Laplacian restricted to finitely supported functions, and just by using some sort of Green's formula, you can see that the domain of the adjoint is those functions in L2 whose Laplacian is in L2. So this is kind of the first thing. So now you're looking at solutions to this equation for lambda negative in L2, and so you look at this, and yeah, so you take such a solution, assume it's not trivial, so take a vertex where it's positive, again, same argument if it's negative, and then you just do this very simple, you just plug in the definition, you see that this is negative, so that means that one of the neighbors has to have a bigger value, that's it. So that's the proof, and like no one had really observed this before, because now you just iterate this, so now you have a neighbor where it's just strictly bigger, and then you just repeat this. And you get a sequence of neighbors where this solution is increasing, and so it cannot be an L2. So that's the end of the proof. So I think like this is like you see this observation, and it's rather it's straightforward. I mean, there's nothing. It's a very easy proof, but it has actual. Again, no one had looked at this. So here is the statement. So that I thought of saying. So even though this is a very simple argument, still no one has told me, yeah, this is very known. So I feel confident 10 years later that I can say that this is sort of a new result that no one had observed. And again, one reason is that, like Matthias said, is once this normalized Laplacian came along and was so nice, and you had this Chigger thing that was really nice analog, people stopped thinking about this unbounded thing. And so this Laplacian is bounded if and only if this degree function is bounded. So you have a uniform bound on the degree of the graph. So this is if and only if. And so whenever this Laplacian appeared in the literature in infinite graphs, this was just a standing assumption, and then these issues never arose. So I think this is one reason why it was overlooked. And so, like I said, so because we're going to come back to this, I just want to say, so the argument just shows that the increase in this kind of solution increases in some direction, but it can still remain bounded. And this will be, when is it bounded will be kind of the thing we look at for stochastic completeness. And a couple other things, so you can, another operator that appears often for graphs is this adjacency operator, which is related to the Laplacian in this way. So you evaluate A of f at a vertex x, you just take the sum over the neighbors. And this might not be essentially self-adjoint. And this was observed first by Mohar and Ladich in 85 and Mueller in 87. And then people got interested. So there's Elenia and Galenia Schumacher. They have some papers about kind of characterizing when is it essentially self-adjoint. So that is. And then more generally, then Matthias came along, and they took this Laplacian that I have, and they looked at a much more general setting where you have weights on the edges and a general measure on the vertices. So not just counting measure or degree measure, but anything. And there it turns out that once you write down this operator, it might not be essentially self-adjoint also. And so I'll talk more about, well, I won't say much more about this result, but then they came along and they have this paper that was published. I'll talk about references later. It's a little tricky to say, but I think the archive version was something like 2009, so about a year after.
May I ask a question?
Yeah, sure.
So if you look at the adjacency operator, so this is like Schrödinger operator, right? The Laplacian plus the potential
Yeah.
happens to be the degree.
Yeah.
And it's unbounded, say. Do people? I suppose there are many results about self-adjointness of Schrödinger operators, depending on what kind of potential.
Yeah. So in this framework, where Keller and Lenz, they have potentials as well. So they cover this, and they're how is it? I think think the growth of the potential maybe helps you or something. They also have criteria that incorporates the potential, so this viewpoint is very, very thorough. Do you want to say something?
There are almost no criteria when
Yeah.
the example where there is, but there's like no, because like the potential is really big.
Yeah. I mean, there is criteria in these papers.
No,
so.
no, only for it's not essential.
For where it's not, okay, that's true, yeah. So somehow, yeah, maybe this is true. So these papers maybe talk about when it fails. Yeah, okay. But anyway, so then when this example of Keller lens came along, then people got more interested. So there's some papers by Colin de Verdier and Toki Hamza and Truk. They investigate some metric completeness and some papers of Milatovic. And this is kind of my first collaborative paper with Matthias and his advisor Daniel Lenz and Sebastian Hasler. So we looked at some when can this essential self-adjointness fail, and when you might have many self-adjoint extensions of the Laplacian, and they might have very different spectral features, for example. So we looked at this, and then ultimately so I will come back to. Well, I won't come back to this, but I'll talk more about these metrics, just like Matthias did, and then ultimately with Matthias and Zhuping Huang, who's a former PhD student of Sasha Grigor'yan and Jun Masamune, we have a kind of a Gaffney type result where sort of metric completeness implies essential self-adjointness in a certain class of metrics. So, which are these intrinsic metrics, which I'll talk more about because they also appear naturally for stochastic. Okay, so this actually proved to be very fruitful. I think this is what I want to say. Is this question that somehow had been overlooked in the literature? There was kind of a big interest after, so this was nice. Okay, so now let me talk about the main question, which is stochastic completeness. So again, this has to do with the heat equation. So if you have a bounded initial condition, so this is what the heat equation looks like here. Again, the time is continuous. This is continuous time heat equation. The space is discrete, but the time is continuous. And you can construct, I mean, again, Gregorian talked about that you can kind of do this exhaustion argument to create the so-called the fundamental solution, so heat kernel, which gives you a solution to this. And so this kind of goes back to work of Józef's on manifolds. And I just transferred it over to graphs because you can do this kind of easily, just by some maximum principles. Or you can kind of use the functional calculus and define this semigroup and kind of extend it to bounded functions and then create solutions this way. And stochastic completeness has to do with whether this, so you always have existence and the question is about uniqueness. So a graph is stochastically complete if this is the unique bounded solution to the heat equation with initial condition U naught. So sort of initial condition, a uniquely determined solution. And you can look at this as a number of different ways, which I learned from a survey paper, like a AMS bulletin article of Sasha Grigor'yan, that there's many ways to look at this. So one way is, again, that you take the heat semigroup, you apply to 1. This is kind of the total amount of heat, or the total probability of finding your random walker in the graph, and this should stay 1, so you don't disappear from the space. So this is also called conservation property. So that's sort of, so stochastic completeness has to do with conservation. Then stochastic incompleteness has to do with loss of heat. So it's like there's some probability that you have such a big growth to infinity that your process gets kind of pushed to infinity in finite time. And again, for the results I'm going to talk about in a minute, and we already saw this for this essential self-adjointness question, you can also characterize this in terms of these lambda harmonic functions, and you look at these solutions, but now you look at bounded solutions. And you can kind of reduce to non-trivial non-negative. And here again, lambda is negative. So again, same kind of equation we saw for essential self-adjointness you see appear here. And now let me talk about, so this was very known for manifolds, and yeah, when we started looking at this, I mean, Józef told me right away, so Grigor'yan has this big article that we can look at, and he said, yeah, you can spend your whole life reading this because it's big and there's lots of stuff, but it's a very beautiful, it has very many ideas, and I really lived with that thing for a year or two. But the optimal result there for manifolds is if you take the volume of a geodesic ball and you have this kind of integral quantity here, so r over log of the volume, this should not be integrable. This implies stochastic completeness. So in particular, you have to have very strong volume growth in order to have stochastic incompleteness. So this is the result we were actually after for graphs. So we wanted to prove something like this for the graph case. So this was kind of the aim. And one thing, so I can also read some other participants. So there's a paper of Dodziuk with Matai where they, in 2006, where, they were interested in other things, but kind of as a byproduct of what they proved stochastic completeness in the case where you have bounded degree. So in this case, this is a bounded operator, and they use maximum principle to show that again, the initial condition uniquely determines your solution. So the goal is kind of like, how far can this be extended? Can you allow the degree to kind of grow? And can we prove this kind of theorem? This was really the goal. So let me talk a little bit about what I was able to do, and then I'll talk about why this kind of result. Well, it took a while, so this will be a story of a number of years, and a lot of some new concepts appearing. So here again, this is just a standard graph metric. You take a sphere of radius r about x naught, and then you look at the maximal degree on the sphere. So this is kind of a quantity that measures how fast the degree is growing, and you can look at this. And so one thing I was able to prove is that if 1 over this degree is not summable, then you have stochastic completeness. So this is in my thesis. And then it was later improved. You can consider only the outer degree. So kind of how many vertices are leading away from the center. So you have this kind of fixed center x naught, and you can kind of consider only a subset of the total degree. And these inner degree and the degree on the sphere actually plays no role. And then Huang also improved this even further. In a paper in 2011, which I'll talk a little bit more. Again, this is he was a PhD student of Gregorian at the time, so he got interested in this question, and I met him while he was still working on this. I will say that it's kind of optimal in the case of trees. So you can sort of for every summable. So when 1 over AR is summable, you can kind of create examples which are not stochastically complete, and which satisfy this degree growth. So I was pretty happy with this. Let me just talk a little bit about the proof. So again, you look at this equation for lambda negative, and you look at the maximum on a sphere of such a solution. Again, you can look at just positive solutions, and then you can show by induction this kind of estimate on how fast it's growing. And in particular, so this is just by induction, it's pretty easy. And in particular, if this is infinite, then this product will also be infinite. Again, here lambda is negative. So this is infinite, and so this cannot be bounded, and so B cannot be bounded, so you don't have any bounded solutions. So this is kind of same idea. It's very easy. You just play around with this equation. So this little equation actually gives a lot of results. And about the optimality, you can also have an upper bound here, which also involves some quantities like this for the case of trees and something that's called spherically symmetric graphs, which are kind of like model manifolds. Okay, so that's the first thing. But let's come back to this Gregorian result. So again, we were really after this thing. So by this optimality, you already can kind of see that there are stochastically incomplete graphs that do not that satisfy this criterion when you look at the volume growth with respect to the combinatorial graph metric. So I was able to convince Józef that you couldn't do this so straightforward, like if you just take the straightforward definition. But he was still not convinced. He was kind of pushing me to try harder. But at some point I was like, I need to finish. Like this is. But then I went on my postdoc and I went to Portugal and I gave a talk, and people again started asking me about this, like, why can't you do this? So I got pulled back in. And so I wanted to really convince people that you really can't do this. So what I did is I created some examples which are called Antitrees, which have polynomial volume growth, so much smaller. So of the order, something like r to the 4 for anything here, and they're stochastically incomplete. So maybe I'll just draw a quick picture. I mean, the idea was very easy. It's actually an idea that's found in Dodziuk's paper with Leon Karp. So these antitrees already appear there, so I just kind of made it look more general. Maybe orange isn't a good color. We should learn from. But anyway, what you do, so here's the example that appears in Dodziuk and Karp's paper. You just take, so you can have any sphere growth you want, and what you do is so this is what they do, so they have 1 vertex, 2 vertices, 3 vertices, and you just connect everything between spheres. So you just make all of these connections and so on. So, and again, you can take any sort of growth. So again, if you take something like where the spheres grow like r cubed, then that will not be stochastically complete. And this is, so I call them antitrees because in trees, right, if you only have kind of like one connection back. So if you cut it, then you disconnect the thing. Here you have to cut the whole thing. So this was kind of my idea for the name. I thought everything in the universe should have an anti. So I thought, yeah, this is the anti thing of a tree. So I thought, okay, so now I've shown people that you really can't do this Gregorian result with the usual combinatorial graph metric. And then it was shown that if you look at the combinatorial graph metric and you take the volume growth with respect to that's actually these are kind of the smallest examples. So there was a paper by Sasha Grigor'yan with Zhu Ping and Jun Masamune, where they show that if the volume growth is less than or equal to r cubed, then this graph must be stochastically complete. And yeah, I should have said that. Again, this is counting measure, so you just count the number of vertices in a ball with the usual. And like I already said, this example actually already appears in this paper of Dodziuk Karp, so I just said, well, like, why not make this grow however you like and see what happens. So this is, so like I said, I was trying to get away from this topic, but then on my postdoc I gave this talk and people were like, why can't you do Gregorian theorem? And I got kind of annoyed and I thought, okay, let me show you how bad it can get. But this was very surprising, I think, when I started telling people that something's really different. And like Matthias also said, there was this kind of need to fix this. And so if you go back, you can ask, like, where in the proof, why can't you do Gregorian's proof in the graph setting? So there's sort of two issues you come across. So one was maybe mentioned, I mean, there's no chain rule. And the second thing is that he uses cutoff functions, which depend on the metric on the manifold. And the kind of estimates you need are not what you get with the combinatorial graph metric. So here, of course, I don't expect anyone to be able to read this. but anyway, so like I said, I was living with Grigor'yan's paper for a while. I mean, the proof is about 5 pages. I looked at it the other day, and I think at some point I was so deep into it. I think if you woke me up in the middle of the night, I could do it. From start to finish, I could actually recreate the whole thing. So I really had it inside and out in my head. So this is just 2 pages, but these are the pages where you kind of start seeing things that you can do with the graph metric. That you would hope that you define the things for graphs, and then you look at what happens in manifolds, and you just follow along and you do. And here are 2 places where things do not go wrong. So here, from this page, I kind of extracted this paragraph, or 2 paragraphs. In any case, so he says, yeah, let this rho be a Lipschitz function so that you have this estimate. For example, it can be a distance function from a subset of M. And then he creates these other functions that he sort of needs in the proof. And again, so this is the kind of thing you already saw in Matthias's talk, that actually the combinatorial graph distance, I'll make this more precise in the next slide, that it doesn't go through. And then here's where you need the chain rule. So you have this line where you have this kind of quantity again. Don't worry about what all these things are. I could have told you 10 years back. Now I don't know, but well, Sasha. But I guess so. He uses, here he has this kind of expression, and he uses, Green's formula here, and kind of distributes the gradient, and then here you have the chain rule, and this you can't do sort of. But let me focus on the first of the problems. So this is again the kind of estimate you need that the gradient of this cutoff function, depending on the distance, should satisfy this sort of estimate. And in the graph case, if you take the combinatorial graph distance and you can define kind of the norm of the gradient this way, which again already appeared in Matthias' talk, this is roughly the degree. It's not exactly the degree, but it's kind of roughly the degree. And so the combinatorial graph distance can be rescaled to satisfy this. I mean, you could have some constant if and only if the degree is uniformly bounded. So again, it's sort of, but once you make this assumption, then your Laplacian is bounded, and by Dodziuk and Matthias' result, you already know stochastic completeness. So again, you don't get this kind of thing unless you assume that your operator is bounded, if you use the combinatorial graph distance. So this was kind of one of the motivating factors to look at these other classes of metrics, which Matthias already mentioned in his talk, these intrinsic metrics, which are well known for Riemannian manifolds, and then for strong and local Dirichlet forms, there's a paper by Sturm where these are studied, and then a counterpart for non-local Dirichlet forms, of which graphs are like kind of the principal example. There's a paper by Rupert Frank and Daniel Lenz and Daniel Winger, which, like I said, it was on the archive in 2011, but I already knew about it in 2009. He saw me in early. So again, I'm going to kind of give, when I give all the references at the end, I'm going to do it chronologically, because then it tells more of a story about how things developed. So what happened is, when I was on my postdoc in Portugal in 2009, I wrote to Sasha Grigor'yan, sent him my paper with these examples of these polynomial volume group, and he invited me to Bielefeld. And when I went, I met Zhuping, and of course I met Sasha for, well, I think you had been here for the Edgar Feldman conference, but maybe we didn't interact then, maybe because I wasn't working with Józef yet, But in any case, I had this paper. So I asked Daniel. I said, "Yeah, I'm meeting, and I have these examples, and I know you have this paper with these metrics." So he sent this preprint to me, and I showed it to Zhuping, and he gave a concrete example that you could work with in graphs, which is the example that Matthias presented, and I'll talk about it anyway. And also Folz kind of also came across these metrics. He was looking at heat kernel estimates. So these kind of naturally arose, and so this definition already appeared in Matthias's talk. I'll use sigma because I want to use rho for the cutoff functions. So this metric is intrinsic. If you sort of sum over all neighbors, the square should be less than 1 for all vertices x. And like I said, so again here, so Matthias had a measure here, the vertex of a measure. Here, my measure is just 1, so I fixed the measure, so that's 1. And again, in the case where if you take the combinatorial graph distance here, you get the degree. So if the measure is degree, then you get actual equality there. In the case where you use the degree measure, but I just used the counting measure, so this is 1. This is the definition, and let me again. What did we want? We wanted to look at this thing. So now you use a cutoff function with respect to an intrinsic metric, and you get exactly the thing you want, because here you use triangle inequality to get this, and then this is less than 1. So this is exactly what you need to do. Well, like one of the things you need to do the Gregorian argument. So these exactly this definition, which again there's a much more general definition for non-local Dirichlet forms, but here, this is the kind of thing you need on the technical level to make the proof go through. And here's the example that Zhuping Huang and Matthias already mentioned. You kind of take the larger of the 2 degrees and you raise it to 1 over the square root, and you can just do a calculation that satisfies. And again, as Matthias mentioned, the vertices of large degree are close to all of their neighbors, which from the viewpoint of the process makes sense because the process moves faster at vertices of large degree, so you get like an acceleration, so you're more likely to see your neighbors. So from the viewpoint of the process, it makes sense. And then Folz proved the kind of Gregorian theorem that if you have an intrinsic metric, and he assumes finite jump size, so you have an upper bound on the distance between neighbors, and then you can define balls with respect to this intrinsic metric, and you take the volume, again, this is just the counting measure, and if you have this criteria, then you have stochastic completeness. So this was kind of, like I said, so there was kind of, it took a little while to prove this, and let me just say that this result is a very direct analog. I mean, it's exactly the right form, but the proof is really not direct in terms of you leave the world of graphs actually to do it. So the way you do it is he does some probabilistic techniques and compares the continuous time random walk on the graph with continuous random time walk on what's called a quantum graph, where you consider the edges to be intervals, and then does some comparison of probabilities and applies Gregorian's result, which was actually extended to the strong and local Dirichlet form case by Sturm, and applies it there, and this is how he proves it. So there was kind of, I mean, I don't know, I thought, so probability is kind of tough for me. So the first question was like, can we do this with analysis? And secondly, can we do it without these quantum graphs? So the first question was answered actually by Zhu Ping in a paper 2014. And he uses Wiko-Mori-Yao maximum principle for stochastic completeness. So there's no probability estimates, it's rather just maximum principles. And then there's forthcoming work of Zhu Ping with Matthias and Marcel Schmidt. They use some techniques developed by Zhu Ping with Shiozawa, which sort of has to do, well, Matthias explained it a little bit to me the other day, but you kind of subdivide edges, so things kind of look local far out. And, but I should say that still, Gregorian's proof has to do with, you prove uniqueness of solutions for the heat equation. You prove a uniqueness class, and this cannot be done for graphs, actually. This is something that Zhu Ping actually showed, that the uniqueness class result actually fails. But you can still get stochastic completeness through other means. So this is, again, so this is still an ongoing story. I mean, there's still kind of things you can do here. So I think this is sign of a good thesis topic, that it's 10 years later, there's still kind of, people are still interested, and there's still kind of questions despite all this work and so on. Okay, so let me talk about some more recent things I did. And this has to do with discrete Ricci curvature. And some work I've done with Florentin Münch, who's a PhD student of Matthias's actually, but he was visiting Yale at Harvard last year, so he came here and gave a talk in our seminar in April, I think, and we discussed some ideas. And so there's been a lot of interest in curvature for graphs in recent years. And there's a couple of different schemes, but one scheme was introduced by Jan Olivier in 2009 for general macro processes, and then it was modified by Lin, Lu, and Yao in 2011. But they look only at this kind of normalized graph Laplacian, which is a bounded operator, and we kind of do it very general. Again, we do it even more general than the setting I'm talking about. We have a measure on the vertices and the edge weight. So let me introduce what I need and kind of define everything. Straightforward way. So you kind of introduce a new vertex measure, which is based on, so you take an epsilon that's positive, and you define this measure, which you can just calculate to be, you get 1 minus epsilon times the degree of x when y and x are the same, and epsilon when y is a neighbor and 0 otherwise. And this, if you take epsilon small enough, you get a probability measure. Here, so it always sums up to 1, but this might be negative, so you have to make epsilon small. So this is, so you have these kind of probability measures on the vertices, and then you, for such probability measures, you can define this transportation distance, which you take the soup over all one Lipschitz functions, where here this is the combinatorial graph distance, we're back to this. over all one Lipschitz function, and you see how much it differs. So this comes from optimal transport theory, that this is kind of this transportation distance. And then you can define, you take 1 minus this divided by the regular metric, and you take the limit as epsilon goes to 0. So again, Livia kind of considered this, and Ling Lu Yao kind of did this for the normalized case, and we do it in general. And this you can say is the Ricci curvature versus x and y, or some discrete analog with Ricci curvature. So I should go fast. Well, I should finish, but I'll try to finish within time. So so this is kind of very abstract. I mean, like I said, it comes from optimal transport theory. I'm not an expert on this at all. I'm very novice. This is a very new topic for me. So, but you can calculate it easily on graphs, and here's how you can calculate it. In some cases, you can calculate it, I should say. So we introduced kind of this gradient thing where you take the difference of the function over the distance between these vertices, and here you take the infimum over all one Lipschitz functions whose kind of gradient is equal to 1, and then you take the difference, the gradient of the Laplacian of f. And here's an easy case where you can calculate explicitly if you don't have cycles, for example. So if x and y are neighbors and they're not part of a triangle or a square or a 5 cycle, then you can calculate this explicitly. So for example, on the integers, this is 0 because everything has degree 2. For like regular trees, like of degree 3, then you have constant negative curvature. So this kind of corresponds to what you would expect in these cases. And then here, so there are results for stochastic completeness in terms of curvature for manifolds. So we wanted to do something similar. So in order to do so, I introduced kind of this minimal sphere curvature. So you look at the minimum over all. So again, this is just a sphere of radius r, and you look at the minimum over all vertices in the sphere, and then you look at kind of all the backwards neighbors, and you look at the curvature between them. And this is what we call the sphere curvature. And again, of course, you could just take the minimum over the ball, but this is actually what you need in the proof. And so what we get is that if you have a lower bound of this form of the curvature, so if the curvature is bounded by some constant, so minus constant times log r for all large r, then you have stochastic completeness. And this is actually a sharp result because we have examples. As soon as you put like a little exponent here, you can show that you have stochastic incompleteness. And let me just to contrast to what happens in the manifold case, there's results of Xu and Varopoulos, where the curvature is bounded below by minus c times r squared, and then you get stochastic completeness. So you see there's a difference. And we were hoping that maybe intrinsic metrics would come to the rescue again, like they've done before, but unfortunately not. So intrinsic metrics, we can also redefine things with respect to intrinsic metrics, and still you get more or less this borderline. So unfortunately, there is some difference here, obviously. But again, this is, and let me talk a little bit about the proof. So again, this is what I want to prove. And you can prove kind of this kind of Laplace comparison thing, where you take, again, this is not intrinsic metric, this is just the combinatorial graph distance, and you can estimate the Laplacian of it, or minus the Laplacian of it, by the degree at your base point minus the sum of the curvatures up to the distance. So this is kind of a nice, but again, you just prove it inductively, it's very easy. And then there's a Kosminski criteria for stochastic completeness, which for the graph case was proved by Zhuping Huang again. And so if you take a non-negative function which goes to infinity as the degree grows, and it satisfies this for some smooth C1 function, which is positive increasing and satisfies this growth, then you have stochastic completeness. And you can, for our case, you just apply it to this function. Well, I should have actually kept the row. Sorry, but I wanted to. I guess I switched off because this is the f I'm looking at. So if you apply it to this, you actually, by our curvature assumption, you actually get this kind of estimate for a function that satisfies this, and this is it. So this is essentially the proof plus this. So it's very easy once you have this. And let me just mention that there's another commonly appearing notion of curvature from what's called the Bakri-Emery formalism, which a lot of people are interested in. And there you also have a result for stochastic completeness by Bobo Hua and Yang Lin from 2017. So what's CDK infinity condition for this Bakri-Emery curvature also implies stochastic completeness. So this is like constant curvature, but we have some decay that we, right? So we have this decay, and they have kind of a constant lower curvature bound. And they also have further metric kind of completeness assumptions that we do not have. So that's just a contrast. And I finished early. That's also a Dodziuk thing that I finished the talk early so that everyone's happy. They can leave. But let me talk a little bit on the references again. I did something where I don't go in alphabetical order, but rather chronological order. So because I tried to tell a story. So again, this is this bulletin article that I lived with for a couple of years, and really could, like I said, to reconstruct some of the arguments in there verbatim for you, which I think is a good exercise. I tell my students actually often that, you know, it's okay to just memorize proofs. That also like changes your brain and trains your brain. Even if you don't understand necessarily the step, but if you can kind of recreate it, at some point you will understand it if you keep coming back to it. So this really influenced me. So I want to thank Sasha Grigor'yan, who's here, for writing this and for putting experience. I think it's a really beautiful bulletin article, and he's also like has a book kind of that has a lot of this. But this was really a very defining thing for me. And then there's this paper of Dodziuk and Matai where I learned a lot about kind of combinatorial graph Laplacians. Again, we were doing something totally different, and all of a sudden we switched. So this paper that Matthias mentioned about the Cheeger constant that Dodziuk has, and this paper were kind of my introductions to this discrete world. Again, here they look at magnetic Laplacians, but along the way they prove like a stochastic completeness result in there as a byproduct of what they were interested in. And again, this is from 2006, but it was already on the archive in 2003, certainly. Then there's my thesis, so I should mention this. So I put it on the archive in 2007, which I'm kind of happy I put my thesis on the archive. I did this so I could try to get jobs, because I didn't. So I think there's two strategies, right? You either write a bunch of papers and then put them together in a thesis, but I did the opposite. I wrote my thesis, and I thought I will now break it up and submit papers. And I really thought I might have two papers, but then Matthias came along and he kind of killed the second half of my thesis. So this essential spectrum stuff, he had much better results. So then it just became one paper. But I did put my thesis on the archive, and it's cited quite often as a result. So I'm quite happy about this. It's my most cited thing, which is cool. So I kind of tried to start a trend there. The theses are a nice thing, and you should read them, not just sitting on the shelf. And then, like I said, then I met Matthias because he came roughly around the time 10 years ago, as he said in his talk, when we had the Dodziuk Fest 10 years ago back, and him and Daniel Lenz kind of extended the setting to, again, allow weights on both the edges and a general measure on the vertices. And they really explored Matthias, for example, asked me the question, if you have a subgraph that's stochastically incomplete with the whole graph, will the whole graph be stochastically incomplete? And I kind of thought, I thought the answer was yes, but he showed me the answer was no. So I think this was not, because for example, just to contrast with transients, if you have a transient subgraph, then the whole graph is transient. But for stochastic incompleteness, I mean, it can happen that this is not the case. This is the paper I wrote when I was on my postdoc in Portugal, where I showed these examples of kind of polynomially growing graphs. So this is kind of there in the story. And then Zhu came along, and he has this paper that appeared on archive 2010. But again, I met him in 2009. And there's this thesis where this explicit example of an intrinsic metric appears. And then there's this paper with Grigor'yan and Zhu and Jun, who I also collaborate with now. So I met a lot of my collaborators during this time. This was very nice. So here they proved that kind of this polynomial volume growth is kind of the smallest you can have. Then there's the paper of Folz, which gives this Gregorian criterion. Again, this appeared in about 2012. And this one doesn't have an archive date because neither of these do, because it didn't appear on the archive. And then this is my paper with Florentin that's that we finished this year, and it's on the archive now.
So
Okay.
what's the Von Gauss and stochastic relationship?
I'm sorry?
The Von Gauss and stochastic completeness relationship?
Here.
Yeah.
Yeah, so this is the Gregorian theorem for graphs.
So it's like polynomial.
So it's exactly, so it's R over the logarithm of the volume should not be integrable. So you need super exponential volume growth, but again, you have to work with these intrinsic metrics. It's not in the graph distance, it's in the
And in your
intrinsic
graph distance for the Ricci bound is below, do you get a volume estimate?
We don't have a way of comparing curvature. We don't have like an implication where curvature gives you some sort of volume growth.
Because you have the Laplace comparison.
Yeah.
But then the
It's-
Laplace comparison proof of Von Gauss doesn't carry that.
Yeah, it doesn't like give a straightforward. Yeah, I would hope that, but it's not. I don't know of any results that relate curvature on graphs to volume growth. Yeah. So this I think is open. Okay, and then I wanted so rather than since I have some time for an ending, so I wanted to say so we've had all these nice tributes, and I think I said